In this lecture, I'm going to give a kind of a basic overview of functions. Now, having gotten as far as you have in mathematics, I assume you have seen the definition for a function many times. And I really hope that this lecture bores you. But let's start. When I was a kid, many years ago, I was taught about functions using a function machine. And in a function machine, one thing goes in and one thing goes out, which is kind of simplistic, but it worked for me, and I had fun drawing the picture and doing the animation. But let's get to the formal definition. Given two sets, A and B, we say that f is a function denoted f colon A to B, which we read as f is a mapping from A to B, if and only if for all little a and big A, there exists a unique little b and big B such that f of A equals B. Let's try this in English. F is a rule that takes every element of A to one element of B, exactly one element of B. If the rule doesn't work on every element of A, then it shouldn't be in the domain. It shouldn't be part of the from part. It isn't a function on A, so you toss that element out and come up with a smaller domain. If the rule for B, this English is screwed up on this. If you have more than one B for the f of A, then it doesn't make sense because then the function is not well defined. Well, is f of A this or that? We don't know. Not well defined. Let's look at some non-mathematical examples. Let A be the set of senators, and f of A is the state that A represents. Well, that's pretty straightforward. Each senator represents one and only one state. So if I said f of New York, we'd have Schumer and we would have Gillibrand. All senators represent a state. So this is a function. Let's change it, switch it. What if I say let A be the set of states, where f of A is the senator from that state? The problem here is we have two senators from every state. So if I say f of New York, do I want Schumer or do I want Gillibrand? It's unclear. It's not well defined. This is not a function. Now let me tweak this a little bit. What if I say f of A is the oldest senator from that state? Well, this is a function. F of New York is Schumer, so it's more straightforward. Let's talk about the parts of the function. When I write f is a mapping from A to B, the domain is A. The codomain is B. It's kind of useless. As long as B contains everything that A spits out, that the function spits out, you're good to go. The range, however, is only what gets spit out. It's only what f produces when it acts on A. Let's look at an example. So I have this function going from the reals to the reals. That's the symbol for the reals. I define it as f of x equals x squared. Well, I can square anything, so that's no problem. F of a real number squared is a real number. But I'm not going to get any old real number. I'll only get positive reals and 0. Okay, so let's go back. We have the domain is R, the reals. The codomain is also the reals. But the range is going to be positive real numbers and 0. We're mathematicians. We don't like writing all this stuff out. And we're not going to. We need to use notation. So one possible notation is I could say, well, positive reals, but I need 0 in there too. So I'm going to union it with a set containing 0. That's kind of clunky. I don't like that. So we're going to use interval notation. Interval from 0 to infinity, where 0 is closed and infinity is open. Open means it doesn't actually include the point, because infinity is not a point. It's a state of being. Or no, it's a concept. Let's do a quick review of interval notation. So let's say we've got this interval. A's on one side, B's on the other, left and right. If I want to talk about all the numbers between A and B, all real numbers between A and B, including the A, including the B, I write it this way. Close bracket A, comma, B, close bracket. That means everything in between, including the endpoints. If I don't want the A in there, I will use an open bracket, an open parent, just to say I'm not including this A. Similarly, I can do open with the B or open in both directions, on both sides. What if I want to go off to infinity? So let's say I've got C in the middle. I want to say C to infinity. I've included the C, so it's a square bracket. You never ever include infinity, so that's a curvy bracket. If I want to go from c to infinity but not include c, again we use an open dot here. And you can use the negative infinity, and I see now that there's not a negative here. That's a typo. Please put a negative in here. Maybe I can do that in post-production. We'll see. And if you want everything, you could say from negative infinity to infinity, or you could just say the reals. That would be easier. When we talk about domain, typically when they say find the domain, they want you to find the biggest set possible. You can always state what the domain is. Like, I have my own function, this is Megan's function, and I decide that the domain is just going to be the integers. It's going to spit out a real number, and my function is f of x equals x cubed. Typically in a domain we say, what can't I stick in the function? There's two types of problems we come across. You can't have zeros in the denominator, the bottom of a fraction, and you can't have negative numbers in an even root, even roots. So the square root is the one we typically look at, but the fourth root or the sixth root, none of those can have negative numbers. Odd roots are fine. The cube root of a negative number, no problem. But it's only the even roots we have to worry about. So let's look at this. F of x equals x squared. Nice, pretty polynomial. There's no fraction, there's no square root sign. I can square any number. So my domain is the reals. If I have f of x is equal to 1 over x plus 2, well, I can get a 0 on the bottom if x is equal to negative 2. So we need a domain that punts the negative 2. So I can write it like this, the set of x, as long as x doesn't equal negative 1. If you want to be really OCD, you can say x element of the reals, where x is not equal to negative 2. We could say the reals minus the number negative 2. I don't think we want to do interval notation because that's messy. That's just too much to write down. What if I have the square root of x minus 1? Well, x minus 1 has to be strictly positive, greater than or equal to 0. So I can put 1 and anything above 1 into it. What about this crazy thing? X plus 3 on top, don't care. I can get a 0 on top, I don't care what's on top, because it's not a square root, so I'm looking at the bottom. Now the bottom is going to be 0 at 4 and negative 5. And it has to be only positives in here, and it can't be 0. So let's set this thing up. Here's my number line. And those are the points where they turn 0. Now in any one of these three sections, that expression will be all positive or all negative. It doesn't matter which number I pick in this section, any number less than negative 5 is going to give me the same thing. For me, the easiest number to check is 0. So I plug in a 0, I have a negative number here, a positive. A negative times a positive gives me a negative. Again, I don't bother actually cranking out what it is. I don't care that it's actually negative 20. I just care that it's negative. If I stick in something bigger than 4, say 50 billion or 10, first one's positive, the second one's positive, a positive times a positive is positive. If I stick in something less than negative 5, like negative 50 billion or negative 10, I'll have a negative times a negative. That'll also be positive. So my domain from negative infinity to negative 5 and from 4 to infinity. I have open brackets on the negative 5 and the 4 because if I plug those numbers in the bottom, I'll get zeros. Zeros in the bottom, bad. Let's recap. A function is a rule taking stuff from one set and spitting out something unique from another set. We reviewed interval notation. The domain is what goes into a function. The range is what comes out of a function.